Okay, in this presentation we are going to look at how to simulate random numbers from the log normal distribution. Okay, this is a Jupyter notebook and the version I'm currently using is 1.6.1 from Julia. Okay, so that's a little bit out of date actually, I might fix it up. So the first thing we're going to do is generate some random numbers, and it's going to be from the log normal distribution. Okay, so first off I'm going to call my packages. Now I have them pre-installed already, but I'm going to use, in this case, distributions and random. Okay, now so that's good, so I can start working with probability distributions, and also I can generate some random seeds later on. That's a minor matter there. So this is the key part here. Essentially what I'm going to do is specify the distribution. Okay, so the distribution I'm going to use is the log normal, capital L and capital N. Okay, and the parameters are mu equals 1.5 and sigma equals 2. Now this requires a little bit of knowledge about the log normal distribution and the parameters that it would use. So there's some prior knowledge about the distributions that I'm not going to talk through in this case. I'm just actually going to run through the process from the point of view of Julia. So anyway, I'm going to save this as dist. Okay, so it's my distribution that I'm using with the parameters I'm setting. And I'm going to use this command to generate 5 random numbers from that probability distribution. I better start pressing these cells just to make them run. So let's just give that a minute. When you're making a recording, it slows things down a bit. But there we go. Okay, so those are just 5 observations there. 19.79, 0.40, 118.41. So there's quite a bit of variety there. Okay. Now, for the purposes of what we're doing, we're going to generate 10,000. And I'm going to use a seed. 1, 2, 3, 4, 5. So that's using the random distribution package, the random package to generate that seed. 1, 2, 3, 4, 5. Okay, so this should be reproducible. Okay, and the command is just like we had before. In this case, what I'm going to do is generate 10,000. So let's have a look at X. I'm just going to start a cell below and just have a quick look at that. Now I won't print them all up. It'll print quite a few up, but there you go. Okay, so anyway, you can filter that out. So what we're going to do first off is calculate the mean and the standard deviation and the variance of the sample we've just created. Now we're recalling that mu is equal to 1.5 and sigma is equal to 2. So the analytical mean is the exponential of mu plus sigma squared over 2. Okay, so let's just run that. Should be about 33 or something like that. 33.115. Okay. And let's see how close our mean is, our sample mean. 32.2851. That's pretty good. Okay. Very minor difference, just sample fluctuation essentially. We can also look at some other ones there. The median, 4.28. Now remember, this is quite a strongly skewed distribution, so there's quite a gap between the mean and the median. But we'll calculate the standard deviation and the variance. The standard deviation is 201.741 and the variance is 40,699.7353. Okay. I could do a little histogram there, and the reason I'm not is partly because it's interesting enough to do histograms separately, and also I don't have it set up right. But this should work using Gadfly, the Gadfly package for data visualization, and just use the command plot, the name of the data set, and what you want. Geom histogram. Here I additionally specify bin count equals 200. I'll do more of those separately actually. It's just when I get it set up right, that would help. So let's look at the interquartile range. Now additionally what I'm going to do is I have random and distributions called. Okay, but what I'm also going to do is now use the statistics package, and the reason for that is I can use quantile. So what I want to do is calculate the mean and the interquartile range, or well, Q1 and Q3. Okay, so the median which should match up with what we have before. Okay, here. Yeah, that's good. That's just a different way of doing it. The quantiles. The first quantile is 1.09, and the third quartile, 16.817. Okay, let's just save those, and we'll calculate the interquartile range. I'm guessing that there is a way of doing that by calling a function, but I want to do it by first principles in this instance. Okay. Oh, no, I have to do that again. 15.7255. Okay. Now, I'm going to compute probabilities. Okay. This is a very interesting way of doing it using bit vectors. So first off, let's call the first 10 values of x. Just use them as an expository case, as a quick example. And what I'm going to do is check which of those first 10 are less than 20. Okay, so I'm going to have an element-wise comparison to see if they're less than 20. You notice that little dot there in front of the less than sign. And I should get a bunch of zeros and ones there. Okay, 0, 0, that corresponds to 46 and 24. Then a series of ones apart from the 0 there that corresponds to the 84.177. Excellent. Let's just see if we can do something more elaborate here. Values of x that are greater than 10, or the first 10 anyway, first 10 values, and see which ones are greater than 10, but less than 20. Okay, so what we're going to do here is create two of these bit vectors and just multiply them out. And that will give us this 10 element bit vector there. So this will return 0 if it's outside that range of values, that interval 10 to 20, but 1 if it's inside that range of values. Let's just go back up here and see what this corresponds to. This corresponds to 10.28, 12.58 and 17.66. Okay, so this allows us to calculate some probabilities. So first off, what we want to do is estimate the probability that x is less than or equal to 16. Okay, let's run that there. The mean of our bit vector returns a probability of 0.7426. The probability that it's greater than 8, 0.3595. And this interval probability here. So this can be done two ways. Just subtract one probability from the other. Find the probability that they're less than or equal to 15, and then from that subtract the probability that they're less than or equal to 7. I get an answer of 14% there, 0.1402, but I can also use this multiplication method there as well. So that's it. That is our simulating random numbers from the log normal distribution.